Hello everyone, welcome to CHEM 1314, experiment number 10. Today's experiment is all about determining the enthalpy of a reaction via calorimetry. So what is calorimetry? Well, calorimetry is used to determine the heat of the enthalpy change for any given reaction. Okay, enthalpy is just a way we measure energy or heat going to or coming out of a reaction. For calorimetry, we use a calorimeter. A calorimeter is basically an insulated container in which we perform a reaction and we can take the temperature before and after the reaction to determine how much heat was released by the reaction. So why do we have to have an insulated container? Well, as this reaction is taking away heat or releasing heat to the surroundings, you don't want that heat to actually escape outside of the calorimeter. So for our purposes today, we can make a calorimeter via 2 coffee cups. Okay, we stack our coffee cups like so and put a piece of cardboard over the top, put our thermometer inside, and now we have a calorimeter that is mostly sealed to the outside elements. Okay, this is going to allow minimal heat to escape from the contents or go into the contents from the outside air. In order to figure out the delta H or enthalpy change of a reaction using our calorimeter, we have to know the heat capacity of the calorimeter. The heat capacity of the calorimeter is given in units of joules per degree Celsius. So how many joules of energy does it take to raise the temperature of this calorimeter by 1 degree Celsius? Okay, that's the whole point of our heat capacity. So, some important equations to know for this experiment are listed here. We have Q of our reaction, which is the heat of our reaction, is equal to the negative heat of contents plus heat of calorimeter. That will be the heat gained or released by your contents plus the heat gained or released by your calorimeter. All right. Now, Q of reaction in our case here is the same as delta H of the reaction. And Q of the calorimeter is equal to the heat absorbed by the calorimeter. So Q of our contents is equal to the specific heat of the contents. The Q of contents, that's talking about what's actually inside the calorimeter. So in our case, for part 1, it'll be hot and cold water. For part 2, it'll be our mixture of aqueous hydrochloric acid and sodium hydroxide. For part 3, it will be the solution we make whenever we take aqueous hydrochloric acid and dissolve solid sodium hydroxide in it. Okay, so those are the contents that we're talking about whenever we're looking at Q of contents. Okay, so to get the heat of the contents, you have to have the specific heat of the contents. So whenever we're dealing with part 1, we're going to use the specific heat of water, which is 4.184 joules per gram per degree Celsius. Times the mass of the contents, which we won't record the mass of the contents, we will actually record the volume of the contents, which for the rest of this experiment we can assume that the density is 1 gram per milliliter. So whatever volume you weigh out in milliliters, that is the mass in grams of your contents. And temperature change of the contents is what we're actually going to be recording with our thermometer down inside of the calorimeter. Moving on to the next one, heat of calorimeter, that's heat capacity of calorimeter times the change in temperature of the calorimeter. The delta T of calorimeter is going to be equal to the delta T of the cold water. Okay, so our calorimeter starts out at room temperature. We add our mixture of hot and cold water to it, and then we get a final temperature that's higher than room temperature. Okay, so that difference between our final initial temperature is our delta T for the calorimeter there. When it comes to Hess's law, you want to find a way to make 2 equations into a third equation. So how can we rearrange equation 1 and 2 to where when we add the 2 equations together, we get things to cancel out, and we get this third equation. First of all, on this third equation, we see that we've got solid sodium hydroxide on the reactant side and aqueous sodium hydroxide on the product side. So when we look back up at these top equations, we need to keep the solid sodium hydroxide on the reactant side, and we need to move the aqueous sodium hydroxide over to the product side. So we do that just by literally flipping the equation. So now instead of HCl plus NaOH, we have NaCl plus H2O in our reactant side, and the HCl plus NaOH has moved over to the product side. Notice here, whenever we flip this equation, we also flip the delta H. Okay, so instead of being the positive value for this delta H, it's now the negative value. At this point, we can cancel out things that appear in the products and reactants side for our two equations, our second equation and the reverse of our first equation. At this point, we can completely ignore this first equation. So we cancel out our H2O liquid that appears on both sides, we cancel out our HCl aqueous that appears on both sides, and same thing for our sodium chloride. And we are left with solid sodium hydroxide on the products and aqueous sodium hydroxide in the reactants, which is exactly what we're looking for equation number 3. So how do we find the delta H of this equation? Well, it's pretty simple. We add up the delta H values for the two equations that we added to reach this equation. If I didn't have to change this equation at all, if I could have just added equation 1 directly to equation 2 to get this equation, it would have been delta H equals x plus y. But I had to flip the top equation. So now, instead of being x plus y, it's going to be y plus negative x, or y minus x. Okay, so that's how you figure out delta H via Hess's law. All right, with that being said, I can actually move on and start the experiment. So part 1, we have to figure out the heat capacity of the calorimeter before we can do anything else with reacting acids and bases inside the calorimeter. We have to first determine the heat capacity of the calorimeter. We're going to do that by using hot and cold water, and I'll explain it as I go along. So the first step is we need to take 50 milliliters of distilled water, add it to a 250 milliliter beaker, and heat it up to somewhere between 55 and 60 degrees Celsius. Okay, so I'll go ahead, I will measure my water out, toss it in here. Once I hit 55 to 60 degrees Celsius, I turn my Bunsen burner off and I move on to the next part. Okay, so I just added my water here. I'm going to go ahead, get my Bunsen burner going. That is entirely too low, so I'm going to raise this up a hair. And I have no striker. Alright, so I'm back with my striker now after. Okay, so I'm going to go ahead, get my Bunsen burner going. We are up to 60 degrees Celsius. So now I measure out 50 milliliters. So now I will take my 50 mils of room temperature water and add it to my room temperature calorimeter. I will record the temperature of the water inside the calorimeter, and therefore also the temperature of the calorimeter, since they both should be room temperature. Here I will have 50 mils of cold water inside the calorimeter, and I will add 50 milliliters of my hot water to it. My initial temperature of the cold water is 21.7 degrees Celsius, and now I will add my hot water to it. All right, so the hot water is currently at 57.3 degrees Celsius. So I quickly add my hot water to my cold water, put my lid back on, put my thermometer in, and I swirl it until the temperature stops changing. So the final temperature here of my hot and cold water mix is 39.2 degrees Celsius. So the temperature of the cold water has gone up to 39 degrees Celsius. The temperature of the hot water has gone down to 39 degrees Celsius. So in your calculations to find the heat lost by the hot water, that's going to be the Q of contents for the hot water. You take the specific heat of the hot water, which is 4.184 joules per gram per degree Celsius. So you take that specific heat times the mass of the hot water alone, which we used 50 milliliters of hot water. It's 1 gram per milliliter, so we used 50 grams of hot water times the temperature change of the contents. Okay, so that temperature change for the hot water is going to be final minus initial. You've got 39.2 minus 57.3. Okay, so this is going to give you a negative number in joules. It's going to be negative 3,000 something joules. In the question it says heat lost by the hot water. So we can actually record this negative number as a positive. So instead of writing heat lost by the hot water as negative 3,000 something joules, you're going to write it as positive 3,000 something joules. Okay, I'll explain why we have to do that here in just a second. So the heat gained by the cold water, you're going to do as normal. Okay, it's specific heat is 4.184, mass is 50 grams, delta T is final minus initial, so 39.2 minus 21.7 for the cold water. So why do we do it the normal way for cold water and different for the hot water? Well, it makes this equation a little bit easier. Okay, so the heat that the calorimeter has absorbed is going to be equal to the heat lost by the hot water minus the heat gained by the cold water. So the heat lost by the hot water and heat gained by the cold water, they shouldn't be the same. And the difference between those two is the amount of heat that has actually escaped through my insulated lining in this calorimeter and into the atmosphere around the calorimeter. Okay, so I can feel that the calorimeter is slightly warm. That means it's losing some heat. Lastly, on part 1 here, we have to determine the heat capacity of the calorimeter. Once you have calculated the heat gained by the calorimeter, which is Q calorimeter, we're going to take that and divide it by the temperature change of the calorimeter. Okay, remember what I said earlier, the temperature change is the same as the temperature change for the cold water. So you're going to take that Q of calorimeter divided by the temperature change, which is somewhere around 18 degrees Celsius, and you will get the heat capacity of the calorimeter in joules per degree Celsius. So now, moving on to part 2, here we are mixing aqueous hydrochloric acid with aqueous sodium hydroxide. I'm going to go ahead and measure out my aqueous sodium hydroxide and hydrochloric acid. Okay, so here we are back. I already have measured out and deposited 50 milliliters of 1 molar sodium hydroxide into my calorimeter. I now need to take the temperature of the sodium hydroxide. My initial temperature of the sodium hydroxide was 21.5 degrees Celsius, and my initial temperature of the hydrochloric acid is going to be the same. They were both in containers right next to each other. So initial temperature of both the hydrochloric acid and the sodium hydroxide was 21.5 degrees Celsius. So as soon as I mix these two, I will have a solution of sodium hydroxide and hydrochloric acid. And I know the temperature of the solution is going to be, the initial temperature of the solution is going to be that of both of these. So it's going to be 21.5 degrees Celsius. Okay, so I mix these. I stick my cover over the top, thermometer in here, and I swirl it. So the temperature is gradually rising because this is a exothermic reaction. All right? And once this temperature change steadies out, stops rising, and starts falling, I will record that as my maximum temperature or my final temperature of the reaction. So my temperature has stopped changing now, and I recorded it as 28.3 degrees Celsius. So, to do my calculations here, I know that my heat of the solution is equal to heat capacity of the solution times mass of the solution times the delta T of the solution. Okay. My heat capacity of the solution is a little bit different here. It's not the same as water. It's actually 4.02 joules per gram degrees Celsius. I take this heat capacity, multiply it by the mass of my solution, which we measured 50 mils of acid, 50 mils of sodium hydroxide. So we have a total solution volume of 100 milliliters. And we can assume that the density is still the same as water, so it's 1 gram per milliliter. So we have a total mass of the solution to be 100 grams. Lastly, our delta T of the solution, final minus initial, we can calculate that pretty easily. So the heat absorbed by the calorimeter that actually escaped from the solution into the calorimeter, that can be calculated as the temperature change of the calorimeter times the heat capacity of the calorimeter. Okay, so the heat capacity of the calorimeter, that's what we calculated on the previous slide. So you need to use whatever that heat capacity is and multiply it by the temperature change of the calorimeter. So for example, if I found that my heat capacity was 13.6 joules per degree Celsius and my temperature change was 10 degrees, I put those values into that equation and I get the heat absorbed by the calorimeter to be 136 joules. Okay, so 13.6 times 10 equals 136. Take those two, add them together, you get your total heat release. Okay, so you get the delta H of that reaction. Part 3, we're going to take aqueous hydrochloric acid, but instead of mixing it with aqueous sodium hydroxide, now we are mixing it with solid sodium hydroxide. So I'm going to go ahead, pour this out, and weigh out my sodium hydroxide and measure out 50 milliliters of my acid. So we're back. I weighed out exactly 2.000 grams of sodium hydroxide on the scale. Don't ask me how I did it, I'm magical. I measured out 50 milliliters of 1 molar hydrochloric acid. So now the next thing to do is take the temperature of my hydrochloric acid. Should be about the same as the initial temperature last time around. So my initial temperature of this hydrochloric acid is 21.8 degrees Celsius. So now I can take my solid sodium hydroxide that I've already weighed out in here, add my hydrochloric acid to it, and monitor the temperature change. So my temperature stopped rising again, and it stopped at 44.5 degrees Celsius. Now that we have our final initial temperatures and our masses of everything, we can first figure out heat gained by the solution. We do that exactly the same way as we did the previous one, so part 2. However, this time around, instead of having a 100 milliliter solution or a 100 gram solution, we now have a 50 milliliter solution or 50 gram solution, plus the 2 grams of sodium hydroxide that we added, so our total mass of the solution is 52 grams. So 4.02 times 52 times our temperature change gives us our heat gained by the solution in joules. Okay, heat gained by the calorimeter is going to be done exactly the same way as we did the last time. So take your heat capacity of the calorimeter, multiply it by the temperature change, you got it. Total heat released by neutralization is done exactly the same way. Add up the heat gained by the solution to the heat gained by the calorimeter, you get your total heat released by neutralization. Lastly, we have our post-labs. So for post-lab question number 1, just hopefully we know how to convert between molarity and moles. So you take your molarity of the solution, multiply it by the volume of the solution to get the number of moles you have. Okay, so I've got 50 milliliters of 1 molar hydrochloric acid and sodium hydroxide. So I take 1 molar, 1 mole per liter, multiplied by 0.05 liters because I got 50 milliliters, and that'll give me my answer in moles. For part 2, calculating delta H, just know that delta H is given in kilojoules per mole. So how many moles of sodium chloride were produced in the reaction? You need to figure out that, and then you take the total heat released by the neutralization from part 2, divide that by the number of moles of sodium chloride that you end up forming, and that gives you your delta H in kilojoules per mole. Okay, it was an exothermic reaction. You should end up with a negative delta H value here. For part B, exact same thing, except now you're using the total heat released by neutralization for part 3. All right. Number 3 here, you're using Hess's law. Hess's law, you take the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. So those values are given to you in this table on page 5 through, or on page 10-15 through 10-17. So you need to figure out the delta H of the reaction for equation number 1, which is aqueous plus aqueous. You also need to figure out the delta H of the reaction for equation number 2, which is aqueous plus solid. And then you need to figure out the overall delta H via this form here. So your overall delta H is going to end up being y minus x. So look up those delta H values for the products and reactants that you're dealing with in those equations. And you should be able to use Hess's law to determine the delta H of the third equation. All right. If you have any questions on this, definitely feel free to email us. Feel free to drop in on office hours, and we will help you figure out how to do Hess's law. Lastly here, don't forget to use the negative delta H of the reaction for whichever reaction you have to flip. So in our case, it's going to be that first reaction where it's aqueous plus aqueous. Number 4, you're just comparing the delta H reaction values you get in question number 2 with the values you get from Hess's law in question number 3. Question number 5, you are doing the exact same thing with Hess's law, except now instead of hydrochloric acid, you're using nitric acid. So do the exact same calculation you did before, except look up the delta H of formation values for nitric acid in your table to do the calculation. With that, it sums up experiment number 10. Thanks for stopping by this latest edition of Virtual Lab. We'll see you next time.